Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to welcome Tim Menzies from West Virginia University to Microsoft. Tim is actually the co-founder of the Promise conference, and he is author of many papers in the area of empirical software engineering and machine learning. And today he's going to talk about the future of empirical software engineering. Okay.
Thanks, Tom. Thanks for the invitation to come here. Thanks for Microsoft for getting me out here. Thank you all for attending. Are people online watching this that can call in with questions? Email. Oh, afterwards? Okay, now my email's not here. Was it on the broadcast? So if it's not, tim@menzies.us. And I'll be glad to take your questions. This is a prototype talk. We're building up to, Forrest Scholl and myself are doing this talk at ICSI in Hawaii in May. That'll be a 90-minute briefing. So apart from anything I talk about here technically, if you have general comments about where to take the talk or what might make more interesting to a broader audience, that'd be useful. So this is my debugging run amongst a friendly audience. So your comments are welcome. This talk's by myself, Forrest Scholl from the Fraunhofer Institute. We also have contributions from the University of Auckland. John Hoskins and his stuff will be in the middle when we talk about the visual wikis. So just a little bit about us. Forrest and I are the creators of, there's 4 very prominent open source repositories of software. I shouldn't say open source. There's 4 large repositories of software engineering data that everyone uses. There's the ঙÇÖs repo from Nebraska. There's, of course, all the open source repositories. Forrest Scholl had a thing called CBase funded by the NSF from 2001 to 2005. Who's heard of CBase? Okay, it no longer exists. It literally no longer exists. The license fees for the proprietary databases used for it are not paid because there's no funding anymore, so all that data's gone away. The Promise data set, we put it up with WordPress on DreamHost, and I think I paid $20 a year to keep it going. And the idea there is that if you publish it, if you publish a paper at the Promise conference, we ask you to offer the data that supports the conference, that supports that publication. And as you can see down at the bottom here, there's we have 130 data sets, and what the conference does is it fuels the repository. It's a very exciting group. Now, based on all that work, what's next? That's our question. What's next? So we want to do more and more and more and more data mining, not just on different projects, but again and again and again on the same project. So the proposal here is not just to learn from a project, but to learn and relearn and relearn. And by data mining, I don't just mean building predictors. I mean automated agents that implement prediction, monitoring, diagnosis, planning, all the things we want to do for adaptive business intelligence. Just a comment about adaptive business intelligence. You may also have heard of this as predictive analytics. A complaint against the software engineering research world is that the most prominent, most widely cited work in software engineering is typically to do with software testing. It's almost as if the software engineering research community has mostly given up on influencing the early part of the software process cycle. We've gone for the end stage where we're not going to hurt the developers too much. We're going to say, you write any crap you like and we'll test it back to conformance for you. I want to work at the unpopular end of the software lifecycle. I want to work at the beginning processes where managers want to make decisions about budgets, about resources that have vast impacts. I don't want to work at the micro level of fixing the if statement. I want to find out if we have enough people to build the whole software. Now, by adaptive business intelligence, I'm talking about learning and relearning. And relearning will be a theme we'll come back to many times. And things like how to detect a death mark project. Not just how to detect something, but how to repair that death march project. How to buy sell points for software artifacts. How to invest more or less in staff training or development programs. How to prioritize software inspections. How to estimate how much it's going to cost. How to change things so that the cost, the number of bugs you deliver, the time it takes to deliver change. These are the sort of things I want to do with my adaptive business intelligence toolkits for software engineering. Now this talk is a plea for industrial partners to join us. It's also a roadmap for about a decade more of research. If you leave this talk with, I wasn't sure about blah, 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 it's because I'm not sure about blah, blah, blah. I'm trying to paint a picture of what I'll be doing for the next 10 years. And if I don't have all the answers yet, well, watch this space. Now, there will be some new results at the end that I think are quite interesting, but hopefully I'm going to raise more questions than answers by this talk. That's its point, that's its goal. I want to talk about data mining and software engineering. I want to talk about all the incredible things that are now pretty routine that researchers do all the time with data mining and software engineering. I'm going to put up 6 categories, and by no means this is the spectrum. This is an incomplete list. So if you're not on this list, I apologize. But there are some people that take software process data. How good are your developers? Are you working on stable platforms? And they do things like generate effort estimates. Barry Beam's been doing this for about 30 years. I've been doing it for about a decade. Martin Shepard's been doing it for about 15 years. And many other people besides. Other things you can do with software engineering, the social stuff, social metrics. For example, work at Microsoft studied which tester do you respect the most, and that was a predictor for what bugs get fixed. And so learning from the social dimensions of our projects. Then there's people that take static code data, static code descriptors of modules, and output predictors for where you're going to find bugs. And many people have done this work. I've done some work here, as well as numerous other people, Tom Ostrand and Elaine Weicker at AT&T, and many others besides. Other work is trace information. You're watching a program running, and you're learning what methods call what. And things you can do here is work out the sequence of errors that typically lead to a bug, or if you've got 2 modules you don't know anything about, you watch them running and you work out the API between them. And this is people like Dao Ji and Andre Zeller and many others besides. Then there's the usage data. What's everyone else using that's working? You're doing a tab completion. You've typed half the name of a method, you hit tab and a list of completions pop up. And hopefully that list of completions is things that generally work in your environment. So people like Martin Rimmelard with the recommender systems study the current systems to find useful parts to explore next. Then you've got all the text mining people that will accept any textual form at all. The way Andy Marcus views the Eclipse code base is a text mining problem. And when he does fault localization, you give him the text of the bug report, and he comes back to you with a prioritized list of 20 to 30 methods to look at, saying this may be where the bug will be. And he's pretty good at it. And the text mining stuff is getting fascinating. We can do things like learn the actual software process followed by an organization, not some CMM dream of what you think the process is, but what actually goes on. Now, the state of the art of all this is, firstly, a lot of this is research and very little hits industry. If data is collected at industry, it's usually forgotten. That's the sad truth. Very rarely kept. And if it is kept, it's usually write once, read never. Another level of stuff, and this is, and as I go down this slide, you're getting to fewer and fewer people, and you're generally stepping away from industry practice into more and more rarefied research. There's a lot of dashboard work, visualizations of feature extraction, but the intelligence is left to the user. So there's many, many software packages that will help you connect to large corporate databases and produce impressive screens of multidimensional data like this. But often in these dashboard-based approach, the final intelligence step is left to you. The fact that you're going to combine features from here and learn a threshold that gives you a rule for action is typically left to you. The last final step of aggregating the features and say, this is our local policy, is not supported by dashboard technology. In some ways, it's like all the stuff we're seeing now, support for massive parallel execution. Very exciting work, certainly needed for the upper level intelligence. Like we certainly need support for distributed file systems, all the stuff you get with HADOP. But even after you've got HADOP or GNU parallels or MapReduce working, you still have to put the intelligence on top. It's like having, I shouldn't say bus in a software organization. Maybe I should say you've built the taxis but not the taxi drivers. Okay, so I want to build the taxi driver that knows how to navigate through. Now it's important that you build the taxi, the roads they're on, all the things the dashboard technology gives you, all the things that the parallel data miners give you. But even after that, there's still work to do. There's a lot of work on data mining stuff, a lot of work done by Microsoft. For for example, all the people in this half of the room. In fact, surprisingly, I didn't know this would happen. But now, what I'm not seeing is the relearning. I'm seeing a lot of learning predictors, but I'm not seeing monitoring of old theories and doing revisions. Now, just a little aside for the geeks here. The instance-based learning people would smirk at this point because they've got a constant review policy. They can just pour instances into their library. But if there's ever a business process of reflecting over the available data and writing down a policy and saying, here, this is the way we do things in this organization, even the instance-based people do not have a relearn device for the policy extracted from their instance space. Although see recent publications by Menzies and Brady. Now, of course, at some point someone says data mining's stupid, data mining gets it wrong. And I say, hey, no one's perfect. Look at all the mistakes people make. Goodness me, data miners are pretty stupid, and people, do you know how dumb they are? Have you read the Wikipedia page on list of human cognitive biases? 38 ways we get decisions wrong, 30 ways we make mistakes with probability, 18 ways that social pressures that cause detrimental social decisions, 10 ways that our short-term memory problems stop us making good decisions. At least with data mining, we can repeat the analysis separately and audit the conclusion, which is not to run down people. Some of my best friends are people. I'm even married to one. What I want to talk about is creating agents of communities, each with novel insights and with limitations. And if we work together, maybe we can shine light on the darkness of each other's soul or something. Maybe together we can find more things than if we work separately. Now, does all this change what we call empirical software engineering research? Well, I think it does. There's a lot of interest in Science 2.0. Ben Shneiderman's call to arms, the growth of the World Wide Web continues to reorder whole disciplines. It's time for researchers in science to take advantage, take collaboration to the next phase, and reap the potential intellectual and societal benefits of having hundreds of thousands of people reviewing data generated. What would that look like? Well, it's not going to be like this. I don't think that once we've got Facebook, YouTube and blogging going, that we've got these things going. The units that I pass around between my collaborators around the world are not, hey, this is the movie I went to. It's units of scientific theory, it's data. I need more tools than Facebook, YouTube or blogging. But it's certainly true that these tools mean most people are online a lot of the time. And these tools mean that underneath them, all the network layer of the internet is available to a lot of people. How does that change the nature of the scientific work? Well, I think it adds roller skates to software engineering. I think what I want to do is use data mining all the time on software engineering data. If you're interested, this guy achieved 80 miles an hour going through here. That's not his speed record. His speed record is 300 miles an hour being dragged behind a car on a flat horizontal space. But this was more challenging, of course, because of the G-forces going around the loop there. Just an aside. Now, what's the difference between what I'm saying and standard software engineering research? Well, I would characterize standard software engineering research 1.0 as follows. It's lots of case studies where you gaze at an organization and see what you're doing. Imagine Margaret Mead going into Samoa. And sometimes there are experiments where we actually change local conditions. And often those experiments have to be on very restrictive case studies. Often the student project where there's 40 people in a university class, we make half of them use Java and half of them use C. We come up with some conclusion. And because the rate of data extraction is small, and because the amount of data collected is very small, often very simple statistical analysis methods which date prior to World War II are used on these things. Now, if you go from here to Science 2.0, then all these people, the case study and experimenter people, become data generator people. They generate the data. And then a large number of data miners are applied to that data. So a small group of people generating data, a much larger group of algorithms analyzing that data. If you doubt that there's 10,000 possible data miners, I refer you to a recent publication of mine in December, Automated Software Engineering, where we list 17,000 different ways to configure instance-based reasoning. And instance-based reasoning is just one way of doing these things. So there's a huge space of analysis methods. It's not like everything's just a t-test. There is a vast space of analysis methods that is mostly unexplored. Happily, if we do crowdsourcing, we have not tens of thousands, but hundreds of thousands of people eager to do the analysis. Every research PhD doing software engineering, faculty members like me, given the ready availability of data mining toolkits, business users from around the world trying to find what is the most important pattern for their data. So this is the crowdsourcing picture of empirical software engineering version 2.0. Now, this, I think, solves a problem with case study-based research. Now, in the case study-based research, I think it's very powerful for defining problems and highlighting open issues, and has generated a large number of candidate ways we might improve a project. If you look at Albert Andre's and Dieter Rombach's 2003 book, you have in this book hundreds of ways which some people have found in some projects improve those projects. You know, reduces defects, delivers early. And you see landmark publications based from the case study-based people who offer piercingly clear statements of problems which researchers might not have gotten to without a clear insight. For example, Kitchenham's TSE 2007 paper asked a question so simple, I went, oh, why haven't I asked that myself before? Cross-company versus within-company estimation. If you're organisation 1 and you're learning something, and you've got access to data from organisation 2, is it more useful to use your own data than someone else's data? Very simple question. And it never occurred to me before someone posed a very clear statement of it. And this has spawned a whole subculture of researchers checking to see if what works here also works there. Now, the case study-based research has limitations. Primarily, it's too slow to keep up with technology. Imagine one case study per PhD, 3 to 5 years. By the time that PhD has finished their case study, written it up, documented it, published it, the world has changed. There are still people doing case studies on pair programming. There are still people studying whether C++ is better than C. Meanwhile, we're talking, functional programming with F#, cloud computing. The case study work cannot keep up with the pace of technology change. The case study work has produced too many candidate methods and very little guidance on what methods to apply to particular projects. If you chose to do all the 107 recommendations of this book, your senior management would tap you on the shoulder and say, can you just give us the 3 that are most important? And you go, oh, but this book offers no guidance on how to pick between these. If you pick up the IEEE 1012 standard on verification and validation, you'll see, I'll get the number wrong, 87 things you could do to do V&V on software. And you won't see guidelines on which is most important for a particular project. You'll also fret about the generality. We know that when people have studied conclusions from one project and taken them to another, they've found very little generality. Tom, who else was on your FSC 2009 paper? Nachi? Nachi? Tom Zimmerman and other people, and Nachi and others from Microsoft. They took pairs of systems. They had 662 pairs and checked if what learnt here worked there. In only 4% of those cases did what worked there worked here. And if you read the Making Software book, Chapter 1, Forrest and me go through literature and come up with lists of the very small number of examples of it worked there and it worked here. And you'll also read in that chapter a vast list of, and by the way, usually it doesn't work here if it works there. So we need to do something to patch case study-based software engineering. We want a partnership. Data mining is pretty stupid. It's got no business knowledge. We need those business goals from the case study-based research. Case study research is too slow. And if you want to check for generality of those case study conclusions, that's even slower. So how about we do case study research on one project to raise questions and possible answers, and we do data mining on many, many, many projects to check those answers. And that, I think, is the future of software engineering. Now, when we do this, we're talking about learning, and we're learning from other people's data. And so we're talking about ways to handle large amounts of data that you didn't collect. So I want to talk now about adaptive agents for handling that kind of thing. Why do I want to talk about adaptive agents for doing data mining and software engineering? Well, this slide's a bit dogmatic. The first slide says there aren't any general rules in software engineering, and quotes Zimmerman. Now it turns out that there are about 5 or 6 general results, and my name's on 2 of them. So I'm the guy saying that there aren't many general results, and I just have to caveat that we have found a few ways to port things from projects to projects, but there's not many. What I think is more likely is there are general methods to find the local best rules. Instead of talking about some overarching theory like COCOMO or CMM across all software engineering, perhaps we need to talk about ways to find quickly the best local rules. And if you're talking about local learning, the questions are, how quickly can we learn the local methods? How much data do we need? How to check when the local methods start failing, like locality might be a function of the people on the project, the current task, any number of factors, market forces. We need to know if our theory, which we had, still holds, and how to repair local models. So I want to talk about adaptive agents that watch a stream of data, learning and relearning as appropriate. I timed this talk at 40 minutes at home, which means for an hour session, we should be at a 20 to 15 minute thinking for questions at the end. So which means you could either interrupt and ask questions along the way or wait for the end. It's your call. There's a very small dedicated audience here. So feel free to interrupt. And if you've got questions and you want to hold them off to the end, that's another strategy you might want to apply as well. So what would a stream of data look like? Well, supposing you're the chief information officer and you're receiving data all the time from the projects, and you're building models that predict for things, and there's some quality predictor, defects, effort, something, and you're watching the data coming in, and you're tracking how good your quality predictor is over time. Well, initially you don't know what's going on. And as data arrives in, you learn something and life gets better. After a while, your predictor starts working for the local project. You've got enough data to make predictions about the local project. And then we'll call that mode 1. At some point, there's a breakdown where something changes. The developers change, the product changes, something changes, at which point you learn again. And after a while, you get good and you've got another mode. And then after a while, there's breakdown. Then you learn again, and then you get another mode. Okay? So that's a picture. That's kind of the mental model I've got here, learning and relearning all the time. Question?
I just don't understand what the y-axis represents, but at those points where you're saying there's a breakdown, why is that telling you that you should relearn rather than telling you that your model's saying something's wrong with the process and the process needs to be changed?
Well, what if your model is predicting good and bad results at the same time?
Oh, no.
So if you can't, so if you can't predict anything about the project, right? You've lost your. Oh, I'm sorry. The question was, how do I know that this actually is model breakdown, and not a fact that actually your quality predictor just dropped? Okay. And my answer was that hopefully my model isn't just a sunny day report guy, but he can look at subsystems and say, that one's going to take 6 months, and that one's going to take 9 months. And it's when you lose the ability to make accurate predictions about good and bad behavior in the project, that's when I go crazy down here. And maybe what I should have done is the y-axis be the variance of the predictions, or the bias of the predictions. What might have been a better measure. But okay, now what's different here? Now, this is not just let's throw data miner to build a predictor. Most of my research prior to about 3 years ago was just this first cliff, struggling to get enough data to learn a mode. I didn't think about what happens when the theory breaks down. It's adding monitoring and repair tools to recognize and handle the breakdown of old predictions. It's about being able to turn to business managers and say, you can trust our stuff, because when we deliver these tools to you, they come with meta-analysis tools that can tell you when they've stopped working. Okay, now if you're doing crowdsourcing, and you have access to a lot of data from a lot of companies, you can imagine this process goes on for many companies, and you're learning modes 1 through 9. And let's imagine these graphs aren't on top of each other, but the first one is 2009 data, and company 2 is 2010 data, and now you've recognized you're here in 2011. Wouldn't it be great to work out that mode 8 looks very much like mode 5 and mode 2? Wouldn't it be great at this point here to say, something, I've entered a mode which has been seen at other companies, at which point you could import prior data and lever the experience base of prior projects. A fool learns from their own mistakes, a wise person learns from other people's. So that's the picture I want to offer you. And there's any number of research questions this raises. Anonymization, how do you share data without revealing confidential information? How do you take a data set, preserve its statistical properties without revealing individuals in that space? And that's a massive research area right now. Techniques like k-anonymization and many more besides talk to that. How do you do scale up, volume of data? If you're working with raw project artifacts, not some pretty summary, but all the emails ever sent during the online discussions on the design. And if you're crowdsourcing, take all that data source and multiply it by 1,000. How do you explain what's going on to business users? If I'm interested in business users setting policy and telling the business users when to revise those policies, I have to somehow take complicated theories and show them in a succinct way to users. And so I can't show them some Markov chain function. I can't show them, the linear combination representing principal component 7, because they'll start blacking out at that point. Typo. Noise from bad data. This has nothing to do with dads here. But if I'm taking data from multiple different sources and I didn't control the collection of that data, I'm going to assume that data's got noise.
I got a question just about your first point.
Non-normalization, yep.
So that kind of, it seems like there's an implicit assumption there that if the research community comes up with a decent anonymization scheme, that there are companies that wouldn't have made their data available if it was not anonymized, but would if it is anonymized. But is there an incentive there for companies or whoever that doesn't currently make their data available that now they're going to?
So I'm not sure the microphone picked it up, so I'll see if I can repeat your question. If we solve the anonymization problem, would that solve the data sharing problem? Why would companies want to share? Well, let's say you're the first company in Arizona to do agile development with F#. Goodness me, you might want to learn experience from other people. So the Linux experiment was a surprising success. We can get large groups to organize. My hypothesis is that we'll end up in a period in 10 years from now when we realize we can learn more together than elsewhere. Now, in any other part of the world, they might disagree, but in the hippie Pacific Northwest, we all share hands and go to Burning Man and dance together naked. The line, I won't go on with that metaphor. But you're right, there are corporate policies that prevent sharing. Let's see what happens in 20 years' time.
At the same point, there's the same problem that Science 2.0 has as well, which is that there's really very little incentive for scientists to share their data set. I mean, given that we reward publication and not providing data, far better for me to keep my data set and milk it for as many publications and withhold it from my competing.
So the question was, is there even any precedent in any scientific field of data sharing? It's two replies. Astronomy has rules about data sharing. If you collect data from the sky, you get it for 6 months. You get a period when it's yours. And then you have to get it the hell out to the community because it's from the skies. The PROMIS experiment, when we started in 2006, we said no one, Lionel Brion, God bless him, said no one will give you data. No one wants to give you data. And it turns out to be insanely easy to collect data. Just ask for it. We have 130 data sets in PROMIS. We had 50 new data sets last year. I spent 2 hours with ACM Portal last year, and I found 77 papers using the data sets in PROMIS. So I can point to at least 2 research communities, one of them is software engineering, that doesn't live up to the pessimism implied by that question. Will it mean that all scientific disciplines will share data? Again, going to Burning Man and Dan? No, of course not. But some may.
So the papers that you found, were those not the original papers from which the data sets came? Were those ones that used?
Yeah. If you look for KC1 in ACM Portal, it's all over the place.
That's one of the data sets?
Yeah. NASA 93 was a data set that someone gave me at JPL in 2003. And I can't tell you how many journal articles I get to review that have Coke 81 and NASA 93 in them. And they're all from PROMIS. Okay, well, moving on. Thank you for those questions. Now, what I want to say is that the tasks I want to do can be done by data mining. And why is that important? The sort of things I want to do, prediction, monitoring, planning, classification, etc., I did it in the 90s as part of my PhD. And I did it in a logical framework. Any formal methods geeks here? Abduction, belief revision? Okay, so I was an AI logical guy in the 90s, and I had a thing called, well, let's not even talk about it, but it didn't scale. My precise reasoning with logical primitives didn't scale. The data mining stuff scales. So I want to cast all this business intelligence stuff in terms of probabilistic data mining, and it will scale. Okay, now, so how would I start? Well, this might change after visiting Microsoft, but after my recent visit to Swinburne in Melbourne, I discovered the visual wiki technology that's being put out by the University of Auckland, and this is being used around the world. The CDC in Atlanta is using this, for example. And in this model, everything you've got in the project is thrown into a wiki. Perhaps not shared with the world, perhaps kept behind an internet. And in their model, you can input text, or you can input directed graphs, or you can derive this sort of semantic graph from this sort of text, but rich associations between things. And their technology, you can see an impressive array of different textual forms here, controlled entry for some of the wiki entries. There's even a meta-wiki device they've got for configuring their wikis. Some of these wikis actually have semantics. Down here is the enrollment process for a first-year student at the University of Auckland. This is an executable model in a wiki. Now, once you start giving me business models as part of the visual wiki, I can start doing simulation and learning on that space, a very rich source of data. And so what I want to do is, one more slide. They've even got wiki builders for configuring this technology, so you can build a structured wiki environment for your people. And the idea is that we just give away this stuff, and you can download this stuff from Auckland. And we ask companies to put everything they've got into these things. We also engineer a join key. We give all the artifacts here a unique ID and engineer a join key to some quality measure that you care about, defects, effort, something. And then this is the space we learn from. We learn from the naturally occurring product artifacts. Now you might say that's going to be an insanely large space. I'll just give you a small hint that may not be. You know the text mining problem where you have like 100 documents all written in English, and there might be 100,000 words in English. So if you think about the matrix of documents by text, it's 100 lines long and 100,000 columns wide. And there are really, really, really simple ways of doing dimensionality reduction, really simple ways. This is just one result from some NASA defect data. These were defect logs for 5 different NASA systems, and we applied the standard TF-IDF thing to it. And all we need to know about TF-IDF is it's a linear time feature extractor. That's all you need to know. And of all the words in those defect logs, a very small number of them, here, 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 and here, scored exponentially higher than the rest. So to turn this text mining problem to a standard data mining problem, we just built data sets out of the top 100 TF-IDF words. And then we had a standard data mining set with only 100 columns. And then I think Ripper and J48 was just fine with this stuff. So there's a lot of interesting stuff with text mining, and we're quite happy now to work with unstructured data. Well, this has all been a little bit hand-wavy. Let's go under the hood. Is there any actually technology we can apply here? Well, it's all data mining. If you think about some of the business problems here, here's this learning curve between you don't know what's going on and you do know what's going on. How do you make that as steep as possible? There's a lot of exciting active learning technologies for learning how to find the next best examples to classify. Active learning, for those who don't know, consider you've got the world's greatest obstetrician and you've brought her to the hospital and you give the obstetrician a baby, a healthy baby, and the obstetrician says that's a healthy baby. You do that all day and you realise you've wasted the time because you've only been giving that obstetrician healthy babies, the same label. It would be better to reflect over the space of babies given to that obstetrician and the space of babies you could give to that obstetrician and pick the most informative examples and give 2. How to recognise breakdown. How do I know that this is actually here, the start of a breakdown and not just a mere blip? And we've got some exciting Bayesian anomaly detection technology that we want to talk to you about. How to classify a mode. Well, that's actually the easiest problem. I like Bayes, other people like other things. There's any number of classifiers that can work out what's happening inside a stable mode. How to make predictions. Well, once you're in a stable mode, you've got the frequency counts of that mode. So you can do a lot of what-if queries inside that space. Now, diagnosis and planning, there's been a lot of stuff in logical AI about diagnosis and planning. Let me tell you diagnosis and planning from a data mining perspective. Let's say you're in this mode 3, where your predictions for what's going on are generally worse than 2 other modes. And yes, I understand that this y-axis is badly named, but just go with the qualitative nature of it. Mode 3, our predictions aren't as good as mode 2 or mode 1. It's lower plateau. So if you're in mode 3 and you don't like what's going on, You want to know what happened. We were in this happy place, now we're in this sad place. So what is the delta between mode 2 and mode 3? The delta between the two. Now, if you're in mode 3, once you've worked out you don't like what's going on, you say, what can I do to make things better? And here you've got these two other happier modes, mode 1, mode 2. So what's the delta between mode 3 and these happy places? Now, if I've said that right, by now you're thinking, wait a minute, this is exactly the same process, diagnosis and planning. In diagnosis, it's the delta between a happy place and a sad place. And planning is there's a sad place and happier places. There's also a proviso that in planning, you only care about the deltas that you can operationalize. So it's the delta times the cost of making that delta. And both of these, I think, can be done with a thing called contrast set learning. And also explanation. If you're in this mode and experts say, business users say, we want to write down policies, we want to write a textbook, we want to put something into law, we want to know what to tell our contractors on how to do their practice, what can you extract from this? And you cannot give people the linear combination of a PCA. They just go crazy. So let's talk about bits and pieces. If you ask me, Dr. Menzies, how much of this is working, I say, well, bits and pieces of it. It's all. This is the preamble to an NSF submission. So don't ask for this working on your desk. I can give you bits and pieces. And one thing I can give you right now is the contrast set learner. And I said the contrast set learner was the thing that did diagnosis and planning. Now, the way we got into contrast set learning was we had decision trees with weighted leaves. A decision tree starts at one node and descends, and each node makes a decision and it drives you left or right. And the decisions take you down branches, and some branches take you to happy leaves, and some branches take you to sad leaves. And the Tarzan tree query language, Tarzan swung through the trees, looked for decisions that favoured happy branches and avoided sad branches. And when we tried this tree query language, we took a simulator, C4.5, we did our 10-way cross-validation, and we had thousands and thousands of nodes in the trees. We couldn't even show them to the business user. It was like holding up a picture of quantum dust. The TAR1 returned these tiny, tiny rules, incredibly small rules. So, for example, in one decision tree, we had 45, 93, and 27 branches to happiness, moderate sadness, and total sadness. White is happy, grey is moderately sad, and black is you want to avoid. 45, 93, 27 branches. If we imposed these constraints, and this is Kokomo speak, so analyst experience and schedule pressure, with just those decisions, these things in these small ranges, notice a lot of the branches have now gone. All those branches have gone, all these, and all the sad branches have gone. And over here, I've now got, I've got twice as many, I've got equal number of happy branches as grey branches. Down here, I've got twice as many happy branches as sad branches, and that requires these constraints down here. Now, this satisfied the one PowerPoint rule. My NASA civil servants, God bless them, were busy people. I had to somehow come up with a representation of a complex space, put up on a slide, say, these are your options, this is what you can do. Notice this is 1, 2, 3, 4, 5 what-if scenarios. And here is many, many more ways to happiness and greyness and sadness, but it requires constraining programmer experience, which you may not be able to do. So they cross that one out straight away. And down here, well, here we don't have to do anything with people, we just have to change the specification a little bit in the process. And that gets rid of all the blackness. So they might favour this one, and then you say, well, I want to get twice as many happiness as greyness. You have to change something about analyst experience. This supports the what-if queries. Now, these are tiny summaries of very, very, very large trees. And how is that even possible? Well, it took a long time to work this out, but here's the story, and it's so simple. If you have a decision tree, the higher the decision, the more branches you edit. A decision high in the tree wipes out more things on that side. And the higher you go in the decision tree, the narrower the tree. So the smaller the number of variables you talk to. So it just naturally found very, very small. Now, this leads to a very succinct explanation module. If you ask me how to build a feature detector of graphical objects, where you've got text, horizontal lines, graphics, vertical lines, and pictures, or you've got Boston housing, very low, very high, low, very low resale value, standard learners will produce these structures, and even these, which are pretty small in decision tree land, are intimidatingly large for a business user. The defining moment of my life was I put a tree smaller than this on a business user's table. And they'd spent $20,000 to produce that piece of paper, and they threw it off the table. I was very proud of that piece of paper. I said, what are you doing? They said, well, this only tells me what is. It doesn't tell me what to change. Okay, so I went away and built the tree query language, and then other things happened after that. And for Boston housing, there's 21% of very low resale houses and 29% of very high resale houses. But this single constraint changed the distribution to 97% very high resale, number of rooms in the house and the parent-teacher ratio of the local school. And with that information, you can grossly and simplify your search for high resale houses in Boston. And please notice, you aren't asking the business users to interpret this stuff. You're doing a very, very small thing here. Now, last year, the NASA people were kind enough to allow, it's like 2009, Karen Gundy-Burlett was very kind enough to let my grad students go across to NASA, and we tried this as a shoot 'em up. That we said, what's your state-of-the-art optimizer, numerical optimizer? And they had some very complicated simulation models of flight guidance and control. And please join me in doing a re-entry exercise into the planet Earth. You're going too fast, and so you do a quick dive into the Earth to bleed off speed, skip out again, then apogee, you make decisions, then you come down and you land, hopefully where the ground crew is. And if you can imagine, if you're doing 19,000 miles an hour, small decisions have an enormous impact on where you land, and you want to get here. So what are the decisions, and this is hundreds of variables inside these simulators, that drive you to happy land away from sad land? And the TAR3 treatment learner, that, by the way, is no longer a post-processor decision trees, it does other things that are much more interesting now, ran 40 times faster than their state-of-the-art. These are the numerical methods people at NASA Ames who've got massive supercomputer technology. And our device ran 40 times faster and found better conclusions. And that's something to do with the non-continuous nature of their flight simulators. And better yet, when we produced output, we produced tiny, tiny rules that business users could comment. Of this incredibly complicated decision space, we produced tiny, tiny rules. Now, it turns out this contrast set learner takes us to anomaly detection. The sawtooth was a fun anomaly detector and has a problem. This is Andre Arago, 2005. And sawtooth read data in eras of 100 instances each. And each instance had the same class, seen it, seen it, seen it, seen it. It then computed the probability of the next instance being of that class, seen it. And here you see the average likelihood of seen it as you go through 15 eras. This is 1,500 samples from five planes. In an initial commissioning period, all the planes do the same thing. They all take off, they all bank left, they all bank right. Then they go on 5 different missions, and the likelihood increases at this point because they're going, all of them are just flying patrol over coastal. All of them are just flying through cloud. So their frequency counts increase, and then at era 14, we do something bad to all planes. We turn off an engine, we kill the pilot. And in all cases, this figure drops 2 orders of magnitude. This is not a slight tap on the shoulder. This is a whack over the head saying something's wrong. And we didn't have to tell this device what to look for. It just watched the likelihoods. Now, the complaint against Sawtooth 1 is that it's single attribute. It's based on a Bayes classifier, so it treats every attribute as independent. Sawtooth 2 is a post-processor to TAR3. TAR3 produces these tiny rules, these things that are most important to changing behavior. So don't do frequency counts on attribute ranges. Do frequency counts on how often these rules occur. And you'll get a better anomaly detector, we think. Now, this is very recent. This isn't even dry yet. But we read a mathematical analysis of instance and feature selection, and the statement was that they're the same. In a hyperdimensional space, a cell in a table of data, feature and instance selection is just pushing in the walls. And it doesn't care which way they come from. So we took a long cup of coffee, stared at the wall and said, what does that mean? Okay, TAR3 finds important ranges that change classes and does it very fast because there's some stochastic Bayesian tricks, almost linear time. Actually, I shouldn't say that. TAR4 does it in linear time. TAR4 does it theoretically in linear time. TAR3 theoretically is polynomial, but in practice it's very low order polynomial. Now, what about any instance that doesn't have these important ranges? Just cull them, throw them away. What we realize what TAR3 does is it's a heuristic way of finding the hyperplane between classifications. So if here's data before we apply the pruning of throwing away the rows that don't have the interesting range, and here's the data afterwards, can you see the test instance there? And the green's disappeared. There's a green dot here and here. There's a huge range here. If there's small errors in that test instance, and the error drives it this way, the green's it's going to stay green. Whereas here, if you're doing nearest neighbor, small movements would make it blue, green, blue, green, blue, green. Now, noise has an incredible effect on one nearest neighbor. Here's all these different data sets, and we're increasing the noise in the data set, precision, recall, and you can see it just drops like a stone as we increase noise. Notice what happens to the data sets when we input noise, but we're only reasoning about this reduced space of just the instances that matter. It's very hard for noise to change classification. This dot can move a long way without changing from green to blue. So this instance removal method that's a linear time post-processor to a very fast rule learner gives us noise control. And this also takes us to active learning. This is the diagram I showed you before. Here's class 1, here's class 2, instance of class 2, here's halfway. The most informative examples are the unlabeled examples near these halfway points. And we're doing some exciting experiments with that. And then statistical databases. Preserving the statistical properties of an anonymized data set for a nearest neighbor algorithm means preserving the spatial relationships in instance space. If this is an instance of someone you don't want to put out, there is a huge space in the region cold by what I'm talking about here, where you can create a fake. A huge space where you can create a fake. Okay, so that's the end. So we're after industrial partners that well, unless Microsoft has a better alternative, where we can offer people some sort of repository for their artifacts in any form at all. We're happy to do text mining over large complicated spaces now. And we need a join of those products to some key. And then we need to interview their managers a little bit to get some domain engineering. And all this can happen behind firewalls. We're no longer saying, give us your data and we'll do the analysis. What we're saying now is, we will give you the analyst as an algorithm and drop it into your site. And that analyst will come with a red flag saying, hey, I don't know what's going on now. Give me some more data to change my mind. And in return, we'll give you automatic adaptive business intelligence devices that tunes itself to your local domain. Okay, so if I've done this right, you will have now questions I have no answers to. Because if I've done this right, there's any number of research questions to be offered here. Over to so questions to comments from the audience, and for those folks watching on video, tim@menzies.us for email comments. Over to you. Christian.
Okay, so like halfway into your talk, you talked about how there are a lot of case studies coming down, but because that's only one case study, how they're generalized, and so the solution is to go data mining. How do you, I mean, is data mining just like case studies at scale? How do you, let's say you have some interesting result that you see in a paper from a case study. You say, okay, I want to see if this generalizes to a bunch of things. It seems like there's a lot of difficult steps, because what's measurable in some contexts may not be measurable in other. Right. Thought about this, or?
Well, yeah, but the case studies you see in the paper, that if you pick up Scholl's Guide to Empirical Software Engineering and you read Steve Easterbrook and Margaret Story's most excellent chapter on how to do case-based software engineering empirical research, and it's really good stuff. It really defines perfectly what I'm calling case-based study software engineering. Okay, it's really an excellent chapter. I'm not knocking it, but the amount of time required. So if you wait for the case study-based research, it's the raw collection, it's the massaging, it's this and that and this and that, and years later you get a table with 3 or 4 dot points. Okay, if instead you insert a hook into an active software process, you start mining Visual Studio with no intermediary, you will get a lot of noise, you'll get a large volume of data. Okay, but I disagree that there's not data in unified formats. National government regulations regarding healthcare records. I'm amazed to find out that the guy 3 doors down from me in West Virginia is running a medical health records system which he built to give to remote clinics in West Virginia with a unified data schema. And this particular data collection device is now in use in 22 states in America and 6 Polynesian islands. This is the guy down the road from me in West by God, Virginia. You know, what are you doing to see what unified data sets you can access? You know, so I'm disagreeing with the premise of your question, sir. I think Nachi had a question.
So mine was more after the fact. So eventually, as researchers, at some point in time, some of this will get published in some way, shape, or form. Maybe you touched up and I didn't actually catch it. Sometimes you have to normalize results. So it's okay for the data to be behind a firewall. The analysis can actually be anything. We can find out anything that actually says, okay, this component is going to have 80% failures. But when you publish, you cannot directly publish that a software system is going to have 80% failures.
No. But what you might be able to do in that circumstance is publish a method, sure, and say, look, I can't tell you the conclusions from this company. I've done that. In fact, you might have even reviewed one or two of them, Nachi, I'm not sure, but I've done that where I've said, look, on open source data sets, this is my method, this is the results. Now, the next section I will mark with informal verification. I'm calling it informal because you can't repeat the verification. But this is what happened when I did this inside a company. My ability to predict the errors came within 67%. I won't tell you how many errors I found, I won't tell you the name of the company. Now that paper needs to have, and you guys have actually done this, I've been really happy with, not to suggest I was ever unhappy, but I've been very happy with the Microsoft publications that put out results on Microsoft data and open source stuff as well. Right? Because you can say, here's a technique, and behind closed firewalls, we can't tell you what's going on. But if you want to check if our technique works, here. Okay? So I don't think the barriers that you folks are suggesting, I've got enough examples to say that they're not fatal barriers to all research. Okay? And these examples didn't exist 10 years ago. So extrapolating from 0 to 2 data points, we can go to infinity pretty quickly. Okay, the Promise conference is at ESEM in September. Its due dates are April 10. I'm PC chair for Promise 2011. We're very excited at I said case studies, I shouldn't. We're very excited at industrial contributions. If folks want to produce papers that define a data set and challenge problems, and they want to do some crowdsourcing, they want to get a large group of people working on their stuff, I would encourage the standard research papers, but I would also strongly encourage industrial practitioners such as yourself for putting together challenge problems and writing 4 to 5 page papers describing the challenge problems, current baseline results you're not happy with, and the data sets they came from. So April 17, I think, is the deadline for that. I look forward to all your papers.
Thank you.